today's session is the advanced technology and collaboration for greater project delivery. Our panel today is Patrick Lalonde, who's Virtual Design and Construction Manager for Ottawa and the Atlantic Canada region for EllisDon, and Philip Meadows, National VDC Manager at Modern Niagara. Just to give you a bit of a background on the two, Patrick Lalonde, as I mentioned, VDC Manager with EllisDon for Ottawa and Atlantic Canada, and an instructor at Algonquin College BIM Lifecycle Management Program. As an early adopter in BIM, Patrick started with EllisDon in 2011 and since led the implementation of BIM VDC technology on major building civil infrastructure and heritage restoration projects. Patrick continues to play a key role in the industry as an industry leader and advocate for advances in innovation and AEC technology. Philip Meadows is with Modern Niagara. He is the National VDC Manager, where he leads a team across the 5 offices in Canada that closely integrate with the company's manufacturing and installation teams initiatives, while striving to lead the Canadian MEP contracting industry through the advances in CAD, BIM processes, and technology. He joined Modern Niagara after holding several positions in other firms where he focused on the use of software and hardware technologies in planning, design, documentation, construction, marketing, and management of projects in building and real estate industry. This session, just to give you a bit of an overview, I'm sure that the two will sort of go into a bit more detail, but the general description: technology has become a critical tool on the modern construction site, but it requires the right people and processes to put it in place to realize its true value. This session will talk about new technologies being utilized by both the general and mechanical contractors to achieve better control and efficiency in the field, as well as the processes and agreements that are required to achieve success. So I'd now like to turn it over to Patrick and Philip.
Thank you.
Thank you, Cry. Yeah, so like Cry said, I'm the National VDC Manager for Modern Niagara, where I lead a team of about 35 VDC designers in our efforts to use as much technology as possible to get ahead and stay ahead on our projects and work with the GCs and the other sub-trades on projects. So what I'm going to talk about today are three things that we, 3 of the things that we do. There's more that we do, but just focusing on 3. And so I'm going to start that off with our sleeving process. So for those of you who don't know what sleeves are, it's basically a penetration through a wall or a slab or other part of the building, usually in concrete, where you can pre-plan where you're going to run pipe and conduit and ductwork. We generate these in our model, coordinated model, to try to save time in the field and save money, because it's very expensive to core things later on. We basically do this along with several other point types in our model. We do it for sleeves, we do it for inserts, we do it for carriers and hangers and things like that. So you can see in the slide here, we try to coordinate all of our services together, including the hangers in the model, so that we know what we're going to get to in the field. We take that data, and in the case of sleeving, we have several Dynamo scripts that we run to basically assist us in tagging this. It's very important for our guys in the field to understand where the sleeves are going, what they're for. And so this is just a sample of a project that we're working on out west, where we have fairly detailed information on every tag of what every sleeve is going to be for. We basically use the model data as out in the field as well. So we export the data, point data, out to a Trimble robotic workstation or total station, and the guys in the field are then able to use it to lay out the sleeves on the site. And you can see an example in the upper right there where there's some sleeves placed before the concrete gets poured. The reason we try to do this early on is we can avoid coring. Coring is very expensive. It takes a lot of time. It's not very easy to do. As you can see on the right, there's a lot of conduit and in-floor services that are going to be in this slab along with the rebar. So after the fact, to put a hole in there would be very expensive. A typical small core cost is 1.5K. And when you have a really bad day, coring can cost upwards of 25K. In this example, we just had 200 millimeter cores, very small cores, but it took a lot of effort to get those in. So we had to jackhammer concrete out. We had to revise the rebar. We had to put in the cores themselves, and then we had to refill it back with concrete. And so it can add a lot of cost. So if you don't get the sleeving in early on in the project, you're gonna pay for it a lot later. So in a current case study, this project out west, currently we have 10,000 plus sleeves going in and 200,000 plus pre-inserts. To date, we've done 11,000 sleeves successfully, and we've only had to do 87 cores. So it's actually a very, very good effort on that project. Our previous project was a 90% accuracy on our sleeves, and this one's 99% plus. So we're saving a lot of time and money on the project by being ahead and getting those sleeves in the right place from the model. And then you can see an example here. This is a linear accelerator vault for a hospital. The concrete's radiation shielding, so it has to actually be approved by the Nuclear Safety Commission. So you don't want to spend any time getting that one wrong. It's going to cost you a lot down the road. One of the other things that we're doing a lot of, or we're trying to do more of, is getting into prefabrication. In this particular case, it's some ductwork for a hotel project. So there was a lot of repetition. We had, I think, 42 risers of ductwork that were all the same. So it just made sense to just build those all offsite and ship them in floor-by-floor sections that could be easily installed on the site. In this particular case, we coordinate our model very closely with the general contractor and the subs. Once we have that coordinated, we model it in Revit. In this case, we're using Siskiyou, which is a Trimble product to allow us to make fabricated parts. And then we collaborate with our foreman to figure out where we should break all of our duct into prefab parts. And then we spool it in the software, basically make these sections, and then we manufacture it and assemble it in our shop. We ship it to our site and install it. It's something that a lot of our foremen are seeing advantages on in the field. They took a while for some of them to come around, but they definitely see the benefits. There's advantages when it comes to scale. So if you're doing 42 of something, it's easier to just kind of manufacture it in a production line like you would a car. The other is quality control. You have better results on your connections in the shop than you would on a scissor lift out in the field. And then health and safety obviously is another one. We can pre-build these, especially in the age of COVID, and pre-build most of it in the shop in controlled conditions and then ship it onto the site where we have minimal people having to be involved in installing it. It also keeps the site clear, so you don't have as much material waiting around to be installed. And then the third thing that I'm talking about today is our model to fabrication workflow. In this particular case, it's a kind of an interesting piece, but this can be applied to any of our large piping projects. This was a flume for the University of Ottawa. Basically, they're running water through this piping, and then it gets pushed out of this hole array and they're using it to study erosion at the University of Ottawa. In this case, it's a 24-inch pipe. It has two 16-inch feeder pipes that connect to the top with saddle cuts, and then there's 182 2-inch holes that are punctured into this 24-inch pipe. In the past, we did one of these before, and I think it took a week and about 20 different hole saw blades to get through. And in this case, we were able to model it in the software with fabrication parts. We spooled it in our manufacturing platform, Stratus, and then we were able to directly send a file from the model to our pipe server in Toronto, and it cut it on pipe server in about 20 minutes. We assembled it in the shop and shipped it to site. So again, more prefab. With that, I'll turn it over to Patrick to talk about the other collaboration that we're doing between GC and subtrades.
Thank you, Phil. Yeah, so I'm going to kind of pick things up here and talk about things from more of the general contractor's perspective, and how we set up the process on our construction sites to manage the different multidiscipline trades and the different 3D models available to bring them all together and to facilitate that coordination right through to project delivery. So from the general contractor's perspective, we're mostly interested in a few major things. We are responsible for managing multidiscipline subcontractors. We're responsible for the management of various suppliers, site logistics, the overall project schedule, and ultimately the overall project budget. So we've got, when it comes to BIM and when it comes to establishing these processes, we want to break it down into a few core principles. And technology is absolutely a big factor in it, but also getting the right processes put in place, and having the people that are trained and educated and willing to participate in these processes. So you need to have these three main categories to make sure that the overall process is going to work efficiently. So I'd like to kind of map out the overall process and a bit of a timeline. And there's a few major critical milestone activities that need to happen throughout the timeline of a construction project. So first off is collecting the issued for construction or the design intent Revit files or 3D models. Usually those comes from the designers or the engineers that illustrate the design intent. From there, you want to make sure you include the BIM requirements in the subcontractor's scope of work to make sure that they are going to participate in providing all of their 3D content to the overall process. Once the subcontracts are signed, then and all the players are on board, you need to initiate a kickoff meeting between all the participants to establish the ground rules for how you're going to exchange the 3D data and how you're going to collaborate. From there, you want to capture all this into a BIM execution plan where you sort of document the process and the roles and responsibilities of each party. Once that's established, you can get into the model coordination to start to feeding, developing the model to fabrication level detail and coordinating all the issues and errors. Once you have a coordinated model, you can you then have a product that you can use on site to facilitate installation and quality control. And then the last step is closeout. And closeout can take many different forms, but for the most part, all the 3D data that has been developed over the process gets packaged or converted to whatever format is going to be used for downstream. So I'll kind of talk a little bit more in detail about all those key steps. So collecting the 3D data, essentially, the design intent is typically done in 3D design software, just like we would receive a drawing roll of paper when they get issued for construction. We're also receiving the 3D models. So we need to make sure we collect all the available 3D content that has been developed during the design process. And then in the subcontract, the BIM requirements in our subcontracts, typically, you put those requirements in the major trade contractors, being HVAC, plumbing, electrical, fire protection, and structural steel. And in those requirements is basically outlining, what the submittals look like, requirements to participate in the BIM Execution Plan, what the 3D fabrication model submissions should look like, what the 3D submission process looks like, and then any sort of ownership or proprietary information that needs to be protected. And then next is the kickoff meeting. So generally, this is just an overall list of the types of people that would be participating in that. Typically, you'd want your, sort of the BIM lead from the general contractor, any sort of project managers or superintendents as well. The architects, the consultants, any of the BIM leads from their teams, the subcontractor, BIM leads and project managers, and then the owner or any other participating stakeholders that are key to the BIM coordination process. And then the execution plan. The execution plan is a document that typically outlines three major principles: the uses and goals of the model, the process, and any sort of supporting infrastructure. So the uses and goals are essentially just the intent of, why is the model being developed? What are we trying to achieve with doing this process? Sort of outlines the overall objectives. Next is the process, where you kind of get into the details of what collaboration procedures are going to be used, how you're going to exchange information, and what the roles and responsibilities of the participants are. And third is the supporting infrastructure, being technology requirements, any sort of quality control measures, model structure, zoning, and that sort of thing. So those are the key components. And a BIM execution plan, typically, there's no right or wrong way to create one. It just needs to sort of capture these sort of core pieces of information. And in the execution plan, one of the critical things is getting everybody on the same page with level of detail. And level of detail is essentially defining expectations. When someone says you want to see a model or a BIM model, that's a very open-ended statement. So the level of detail helps define, what that BIM model looks like and what the information that resides within it. So typically, design goes through levels 100, 200 that illustrate the, schematics and overall concept. And then when we get into the construction, we're typically dealing with levels of detail between 300, which is design intent, 350, which is a little bit more detail on exact routing, and then fabrication at the LOD 400, which is what Phil has talked about with the the direct to CNC type process there, where we're actually dealing with parts and pieces that have been prefabricated. And then LOD 500 is in the operation and maintenance side, where you start to plug in more of the intelligent data, maintenance records and things like that to the model objects. So in the BIM coordination phase, typically what we're doing is we're collecting all of these models from the various sources and putting them together to review and to highlight any constructability or clash interferences. And when we bring all these models together, we're also bringing the people together to review and to identify any of the issues that we're finding, and then help resolve them as well.
Yeah, most of this is being done remotely now.
Exactly. So That's one of the benefits of having everything in the model in this sort of virtual world, is that, without not necessarily being in the physical room, everyone could be in their respective offices, all collaborating on the same model together. So a little bit of what that sort of process looks like. I'm kind of breaking it down into sort of 7 major steps, where step 1 being is model submissions, where models are submitted from each of the participating parties from their respective model authoring softwares. Those are all merged together in a platform such as Navisworks, and then published and distributed via, in this case, a software called Revisto. So that would be step number 1. Step number 2 is model review and clash detection. So using those tools to actually look through the model and find any issues. Once issues are found, then you want to manage those issues. You want to identify who's responsible, tag them with any sort of priorities or any sort of information to help you to sort and filter those issues. From there, you can have your coordination meeting. You can bring everyone together and you can run through your list of issues and to resolve and come up with an action plan on how to fix them. Which brings you to step number 4, where everyone sort of goes back to their respective model authoring softwares and they fix their do model corrections. They fix the issues that has been discussed in the meeting. And then in number 5, we have model resubmissions. You resubmit the models, you merge them together, and you publish them. Step number 6 is you validate. You go through those same issues and verify that they've been fixed. You update their status, and then you meet again in step 7. And this is a bit of an iterative process where you're sort of repeating this over and over until you have a complete coordinated model. Which sort of brings me to the scheduling aspect of things. So, you have a BIM coordination process that is sort of cyclical, and you're going through this week by week. And you want to make sure that you have completed coordination so you can get into fabrication and installation. And fabrication, typically has a lead time, and installation usually has a defined date in the project schedule. So you sort of need to work backwards from that defined installation date to make sure that you've completed the BIM coordination for that area with enough time to facilitate fabrication and have the pieces delivered to site to be installed at the defined time. So just a bit of an overview of what that all looks like. We have on the left we have design intent models that are typically not brought up to a higher level of detail for architectural and structural concrete. And then for fabrication level of detail models, we have structural steel, HVAC, plumbing, electrical, and fire protection. And these are all coming from their respective sources. And these model updates are getting funneled to the lead BIM coordinator on site. That's going to be combined and then pushed to the field. And also anything that's being inside the model is communicated back to all the different parties through Revisto. So, and installation and control. So once we've completed our BIM coordination process, we have a fully complete coordinated model. Now we have this product that we can use in the field to help our execution teams and our installation teams build that what we've coordinated in the model. So this is a huge part of the process, because we want to make sure that all the work that we did at the front end gets carried through to the rest of the construction project, so that the execution is efficient and coordinated as possible. So these are just some examples of how we're leveraging those models on site, and how we're carrying through that previous effort of coordinating right through to installation and construction. So here's some more examples how the model is a critical tool on our construction sites to make sure that everybody's on the same page. And here's an example of some underground utility work where we've coordinated all of our underground electrical conduits, plumbing, structural concrete. So now we're able to sort of execute that work very rapidly in the field. So similar to what Phil was showing, this is a modern EllisDon modern Niagara project here, where we have the installation team have their GPS sticks out there, and they know exactly where every pipe goes and where every bend goes. They're not out there, making decisions on what to do next, or to bend left or to bend right. They're just purely focused on executing the work and to installing things exactly where they need to install them. So this allows us to maximize our time on site and make that installation process as efficient as possible. So to reference back to that schedule again, we have our BIM coordination process that takes place virtually in the model, which gives us time to fabricate directly from that model, and then the installation process can take place exactly the way that we've developed it in the model. So here's just some other examples on what that looks like, and keeping that continuity from the model coordination and carrying it all the way through to construction. And I think to tie that into what a bit of the topic of today's event is on digital twins. Essentially the model is a digital twin of what we're building, right? So coordinating and maintaining that twin all throughout the project is a critical aspect of it. And images like this really show how keeping that continuity between model and reality is essential to the entire process. So yeah, I think that's all we had for today. I think we're doing pretty well for time to leave a little bit for questions.
Well, thank you, Philip and Patrick. We do have some questions that have come in here. Thank you, everyone, for contributing those and upvoting them. So running through the list, first question from Peter D. When is the best time to start model coordination on large projects where the design is still being changed?
Well, I think it's in our motto at Modern Niagara is get ahead, stay ahead. So we try to coordinate early on as much as possible, even if the design is going to change. I mean, we're in the middle of a project out west where, unfortunately, we didn't have the staffing in place ahead of time, and we've been catching up the whole time. So to get your staffing preloaded on a project is critical. Obviously, things are going to change, and you're going to have to eat some time there, but you're going to save money in the long run when you have everything coordinated in areas that are not changing, right? So. Yeah,
I just to second that statement, there's no right time to start anything. The right time is now. And that's just the risk, the nature of the business, and the risk you take. You don't want to wait to start coordinating for the design, because you could end up on your heels when it's time to start construction and not be in a good place. So it's better to just start as soon as possible and to manage those changes as best as possible.
Okay, thank you for that. Looks like Mohaded asked, what's your advice for the current industry professionals working with traditional coordination ways who want to make a shift into the digital twin era using BIM technologies on an individual level?
Well, I mean, I think in a lot of cases, at least on our side, sometimes people are not, some of the sub-trades or the designers are not doing a BIM model, but we need to coordinate against something. We need to clash detect against something. So we end up modeling some of that ourselves because it's going to save us time in the long run. So my advice would be to model it if you can, and if you can't, try to get your mind wrapped around the hard parts. So if there's a mechanical room that you have to coordinate, focus on that, and then the rest of the project can be stick built on the site if need be. But pick your battles.
Yeah, absolutely. There's a lot of projects where, we start and there is no available 3D data, or there was no sort of pre-existing BIM strategy. So we sort of need to assess each of those projects by, what we can do with the resources we have, and what makes sense to provide the best outcome for the project. So, if we do need to segregate off an important critical path zone of the building and say, hey, we're gonna model this room and this room only, then great. It's a good way to sort of get started with minimal resources, and then kind of build up your expertise from there.
Yeah, and you might find that you save money later on in the project if you take the time and spend the money early on in the project to get ahead on some of that, or even facilitate some of the BIM modeling yourself.
Okay, and there's a question here that pretty technical. Why SYNQ for Revit is chosen over Revit Fabrication for spooling and manufacturing in shops? Are there any methods to rectify the model which got modeled in metric systems but should have been modeled in imperial? I think that might be two different questions.
Yeah. But okay, so I'll address the first one. We're using SYSQ on a number of projects because they were already in SYSQ when I started. We had 5 offices, or we have 5 offices in Canada. We didn't have a national department before I joined at the end of 2018. We saw the need to kind of focus our resources and form a national group. And so we were stuck with SYSQ on a few projects. And then due to our alignment nationally with our manufacturing side, we're going to this manufacturing platform called Stratus, and it works way better with fab parts in Revit. So we're going down that path, but we have to finish the projects we're currently on in SYSQ. We can't switch midstream unless there's a good break. So that's one of the reasons we're using SYSQ right now. The second question about starting a project in metric when it's been in imperial to begin with. Well, on the mechanical side, it's interesting because we're both metric and in imperial at the same time. You cannot buy a metric pipe. You cannot buy metric spiral duct. You can manufacture spiral duct to other sizes, but I wouldn't recommend it. All of our machinery does metric sheet metal for the rectangular duct and fittings. So in our environment, we're running both at the same time. We have a metric database, but all of our piping is imperial sized, even though the guys on the job site will say, give me a 300 mil pipe. It's actually an imperial pipe. So they just refer it to the rounded metric number. So yeah, starting a project in metric is kind of what we do to begin with. We don't start any projects in imperial. We do have a couple jobs, I think, out in Vancouver that are imperial. So we have to have another database that works with that. But yeah, it's not an easy thing to deal with being in Canada, where you do have kind of your foot in 2 different worlds, unit-wise, at least on the MEP side.
Okay. Patrick, do you have anything else?
No.
Okay. I'm going to jump down to one of these questions just because I find it intriguing. On smaller projects, how are you seeing some of these principles applied? And is there a dollar value or project size threshold where below you feel it's more difficult to apply some of these principles?
Yeah, I can speak to that. I hear that sort of minimum dollar value thing applied where, if it's 10 million or under, we don't do BIM, and if it's, above 10 million, we will. I don't necessarily believe in that. Like BIM is more of a process and a mentality than it is anything else. It's more embedded in the operations of that company. So, you're either doing it or you're not on all projects, in my opinion. But on smaller projects, you do need to you need to adjust your approach or your strategy because you have less resources, right? Or you have less room for budget on tools and software and things like that. So, sometimes, a typical coordinator or field engineer might need to pick up, learn how to use the BIM software to collect the models and to do a little coordination work. And then so you might have to share a role with a person instead of having a dedicated, BIM lead on that project. You just gotta, find a way to be efficient with your resources and to make sure that you can use the tools to make it happen. A big component of it is as long as the design has been done using a 3D platform or a model authoring software, then it's very easy to take it to that next level, to bring it through to construction. It does require a bit more work if the design has been done in 2D and you need to bring up the architectural drawings to a 3D platform. Then you need to invest some time, and you need to make that sort of business case and say, hey, are we going to invest this time to convert our drawings from 2D to 3D just so we can do BIM, on this little renovation project? It might not make sense. So it's just a case-by-case basis on what data is available and what the project risks are and what resources you have, and then you go from there.
Yeah, I'd like to add to that too. Contractually, if BIM is required, you have to do BIM. But if you don't, then you have to take a look at it. Does it make financial sense on a special project where you're just doing like a mechanical room retrofit? Does it make sense to model it because you're going to save time by pre-manufacturing it? So you have to, like Patrick said, take it by case-to-case basis. And in some cases, it's not required. In other cases, it just makes sense to do it if you have repetition, or you can save money otherwise.
Okay, thank you very much for that. We're just running down to the last 5 minutes here. I think we'll take one more quick question here. There's still many trade contractors who don't have the capability to deliver detailed models with sleeves, etc. As a GC, how do you help those trades to bring it up to the required level?
Yeah, it's a good question. Typically, we do it of two ways. We know that in the industry right now, there's a lot of trade contractors out there that don't have the the sophistication or the resources to have a VDC department or all these expensive softwares. So we try to work with them as best as possible. We highly encourage that they take the opportunity to invest in themselves to maybe buy the software or to hire the people or to train the people. And if that's not an option, we do usually have a host of third-party resources that they can sort of outsource the BIM portion of their contract to be able to provide that compatible data to make the process move forward. So that's typically how we work with it, and we have that sort of that tolerance where if we'd rather kind of go through the growing pains with a trade contractor to help them get up to speed with BIM than to have them outsource it. So we're willing to work with them and to help them during those early stages to learn that BIM process and to integrate it into their firm.